Well, so before I start, I'd just like to say that I'm thrilled to be here together with my friends from Germany in at least a symbolic support of our Ukrainian friends. I hope at some point we can meet under more peaceful circumstances. So my talk is about phonon-mediated spin-polarized superconductivity in altermagnets. And spin-polarized superconductivity is very unusual in the context of phonon-mediated superconductivity. Phonon-mediated superconductivity is sort of the archetypical superconductivity we have in this world. And they are typically associated with S-wave superconductivity, meaning that, if you go to momentum space in opposite direction, that superconducting order parameter is invariant. It's the same sign. When you have spin-polarized superconductivity, that cannot possibly happen because the Cooper pair has to have an antisymmetric wave function. So if it's symmetric in spin space, it will not be antisymmetric in momentum space. So this is unusual stuff. Nonetheless, altermagnetism are also unusual, and they open up new vistas for us in many body physics. And I hope to convince you that there are some interesting aspects here to focus on. This work is done in collaboration with Christian Mæland, Bjørnulf Brekke, Kristoffer Leron, and Arne Brattås, my colleagues at the Center for Quantum Spectrometrics at Norwegian University of Science at Utah. And what I'll be talking about today, our base is based on these three papers. Two-dimensional altermagnets. So I'm going to be talking about two-dimensional altermagnets. A minimal model for that, and as a friend of mine once said when he gave a talk about this at a conference I organized earlier this summer, if you say minimal microscopic models of altermagnets, you have to be very specific about what you mean, and I will be specific. There are many, many people who have worked on altermagnets for quite some years, actually. This topic is not as, it's actually quite old topic. I'm a many-body guy. I like field theories. I like many-body effects. So that's also something we've been looking into. But my main focus today will be on this paper, which we recently posted in the paper. Motivation for this, of course, is that, as this paper by Lebor and Jairo and Thomas Jungwirth actually shows, it sort of opened up a new vista for many of us. Many of us got excited about this. But as this list of papers show, people have been talking about non-relativistic spin splitting in magnets for quite some time. And in fact, this one is not the oldest I found. There is actually a paper by Rushton from 1965, which we could interpret as being sort of a precursor to all of this. But it's fair to say that this paper from 2025 really sort of blew this thing wide open, and a lot of us interested in this thing. So, thanks. As I said, once we have these systems with these interesting spin split bands, there are really many, many interesting things to worry about, including many-body effects. One of the many-body effects which is most fascinating to us, at least to me, is superconductivity.
Har you visst det först?
Excuse me?
It's just online.
This is scaring the hell out of me. Please mute.
Sounds please, right?
Excuse me? Come on, don't scare me. I was shocked enough for this. There's also it within a minimal model, which is called the Kyiv lattice, which is tantalizingly close by to copper oxide superconductors, but different in an important way. Okay, here's our little cartoon in this paper of an altermagnet in 2 dimensions. This model was constructed to sort of respect these symmetries that Jairo was talking about this morning. Rotations, spins, lots of interesting things. So you do this, now you flip the spins. I didn't flip the spins, but you can do that, and then you're back to your same, what we started out with. This is different from this guy, which is just, translation, spin flip, back to the same thing. Here, in the former case, I did a rotation. Okay, so that's what gives rise to this superconductivity. And the thing that really makes this work in this way is this yellow citer. The second speaker of this morning talked about decoration of a magnetic unit cell with a third non-magnetic atom. This is the same principle. So it's a decoration of a magnetic unit cell, which makes this standard stuff, time reversal, translation, not work. What you need to do is time reversal, rotation. That's what we're going to be working with. I should also mention that we started out viewing this as a toy model. It turns out that, after we wrote this paper, quite a while afterwards, there appeared papers on potassium, vanadium, selenium dioxide. Can you believe that? Which basically is exact quasi-two-dimensional compounds with exactly this type of unit cell, which are claimed to be altermagnets. So no longer a toy model, real model. So that sort of elevated our things. Now, I mentioned something about the copper oxide lattices. All I have to do now to get from my ultramagnet to my copper oxide lattice is that I basically have to say that instead of having these atoms spinful and the yellow one spinless, I basically reverse the roles. So it's like having these yellow spins spinful and the red and blue ones spinless. So now you see the way it works is that my unit cell is something like this. I flip the spin, I translate by unit cell, I'm back to the same state. So this thing is a standard antiferromagnet. So this two-dimensional version of copper oxide lattice is not an altermagnet, whereas this one is. So since this one is sometimes often referred to as an anti-copper oxide lattice. So that's, you might easily wonder, in fact, I think Lever mentioned this morning also, that some of these copper oxides are altermagnets or candidate altermagnets. If that's the case, you basically need to go to the third order. So our little model for this is basically the following. It's very similar to what the second speaker also was mentioning this morning. We have this lattice. There are some spins that are stuck on this lattice. These yellow and red, blue and red spins. And the spin degrees of freedom are given by this capital S here, which are then alternating up and down like this. The electrons, in addition, we have an itinerant electrons with their spin degrees of freedom, which will hop around on this lattice. Importantly, this large localized spin has nothing to do with the spins of these itinerant electrons. These are totally separate degrees of freedom, which makes this a little very simple model for an itinerant antiferromagnet. Now, what I didn't write here, but of course there is in the background, there has to be some sort of Hamiltonian for these metal spins. This is just a Heisenberg model. And the Heisenberg model works in this way. There are exchange interactions between red and blue, between blue and blue, and between red and red. But notice what's going on here because of this yellow decoration. Okay, we have the exchange interactions here and here, but let's look at the exchange interactions between the red spins. Okay, there's one here and here, and then there's one here and here. So these are different because the chemical environment is different. Likewise for the blue. This one is different from this one, but in fact, in a 90-degree reversed order. So for this reason, the magnons of these systems, spin fluctuations, also have D-wave symmetry. Okay, I'm just mentioning that because I'm going to make a little digression from my phonon story in a few minutes. That's why I'm saying this now. But anyway, let's look at the situation where these spins are really frozen up and down and ask what sort of spin structure or electron structure we get. Okay, you write down Hamiltonian. It's a, I have three types of electrons here, here, and here. I write it down in Fourier space. So this is what this mess looks like in the orbital basis. I diagonalize these things and I get my bands. And you can see what's going on here. Here are my bands. This is along the gamma y direction. That's this direction. Here's the gamma x direction. That's this direction. You can see that the spin splitting is opposite in those two directions. So this is d-wave symmetry again, the spin split bands. And the reason that we get this d-wave splitting in this model is that the only place where the spins up or down enter is over here and here. So if I try to diagonalize my bands now, finding the eigenvalues of this 3×3 Hamiltonian is a mess, so I'm not going to write it down. I will see that I get an eigenvalue equation, which is cubic, of course, but with some coefficients of cosine 2ky and cosine 2kx. Let's say this one enters cosine 2kx, whereas this one enters 2ky, cosine 2ky. If I do kx to ky and ky to minus kx, I reverse the role of the spins. I have to flip the spin to get my coefficients back again. Again, d-wave symmetry. Because I'm doing this whole thing. And this is reflected in the Fermi surface. These two Fermi surfaces are taken about, roughly here and here. And you can see that, here and here, I reverse the spins of the Fermi surfaces. These two branches of the Fermi surfaces have spin down. These two branches of the Fermi surfaces have spin up. So it's not like these ovals that somebody drew this morning, one red and one blue on top of each other. This thing is quite different because, they hardly overlap or they don't overlap at all. It's very difficult to imagine that you can translate these Fermi surfaces and get any substantial overlap between up and down spins. And these two Fermi surfaces, okay, was a little larger up and down here. I'm going to focus on this situation. The salient point here is that if I want to make superconductivity now, Cooper pairing out of these bands, the traditional way of doing it, and in fact in many, many cases, 99.9% of the cases, the most efficient way, effective way of doing it is to have zero momentum Cooper pairs. You take one electron here, and you do another electron over here, and you pair them. Okay, they have to have equal spins. So this has to be zero momentum pairing in this case, close to the Fermi surface, must be spin polarized superconductivity. Cannot be spin simple. However you get it, it's the same thing here. The only way of getting spin singlet superconductivity here, or SZ opposite spin pairing, is to have something sitting here and pairing up with something over here. This has to be finite momentum pairing. Or Larkin-Ovchinnikov, Pouliot-Farrell, really, really flimsy stuff. So we're going to concentrate on how to get zero momentum Cooper pairing out of electrons living on the Fermi surface with whichever means. Okay, let me do a little digression on the story. Let me try to do magnons first. I do spin fluctuations. Is that an air raid alarm?
Yeah.
But we're okay. Should I go on?
Yeah.
Okay, fantastic. Slava Ukraine. So now I actually let these spins fluctuate. And of course, those fluctuations will kick the electrons and do something to do. Here's my little digression first. By the way, here are my magnum bands. You can see the d-wave splitting. Fermi surface up and down. Okay. This coupling will give me some little interaction vertex between electrons and some magnum coming in or out over here. And I can make this into an effective interaction between electrons. Let's try to do it on the Fermi surface. So I do opposite momentum pairing. This has to come up. The way this has to do is that I must have, otherwise it doesn't work for the magnet because the magnets have spin, right? They must come up in with opposite spins, otherwise it doesn't work. So this process will not work in an altermagnet. It is forbidden. One magnetic change will not work because of the spin structure of the firmer surface in the altermagnets. What you can do is to use a double magnet process, because a double magnet doesn't have spin. One has spin up, one has spin down. That doesn't work. And in fact, we investigated this possibility also in this paper. It turns out that if you try to do this and you want to crank up the interaction between electrons, essentially by cranking up this coupling constant to get large TC, you have to go to Eli-Ashburg's theory, strong coupling theory. And Eli-Ashburg theory comes with its own little things. It modifies the quasi-particles that you make the superconductivity out of. And in some cases, this will have detrimental effects on the superconductivity because you basically destroy these nice electrons that you're trying to make super pairs out of to some extent. And the result of this little calculation is as follows. Here are the superconducting gaps I would get in BCS. Weak coupling BCS theory with a double magnet process. Okay. It's, by the way, so this is this. If this firmer surface is upspin, then this is a spin polarized Cooper pair, but it has opposite sign here and here. So it's a p-wave superconductor. Opposite momentum, opposite sign. And this would be same thing in here for, let's say, down spin polarized firmer surface. And these two cases are just firmer surfaces a little bit below and above zero again. This nice firmer surface that I have. If I'm honest now and do strong coupling BCS superconductivity, not BCS, but Eli-Ashburg theory, modifying the quasi-particles, doing the many body effects, roughly speaking, that picture survives. Not quite. You can get actually higher angular momentum pairings, always odd, but in higher angular momentum channels, depending on what the chemical potential is. But this is no big deal. I think the salient point is this, focusing on this picture. Here you can actually get the TC from some Allen-Dynes formula, or from some direct calculation solution to the linearized Eli-Ashburg equations. Not terribly impressive. I think the most important point is that if you look at this blue curve here and read what's written here, many body effects kill the superconducting TC by a factor of 500 due to many body effects. And they are particularly detrimental because you need this double magnet process. One boson process would be less severe, but when you need a double magnet process or double boson process, it's terrible. So you can try to crank up your coupling, but that's going to self-defeat in terms of TC. So next question then is, well, can we do something else? Can we try to do phonons? That doesn't have spin, so maybe we can get away with one phonon exchange. Maybe this process would survive because the phonon doesn't carry spin, and we can actually have both up spins here. That was a motivation for this. And you can actually build a phonon model for this Kyiv lattice quite simple. You just use these symmetries. I'm running out of time here, so I'm not going to spend much time on it, but you have, let's say, this one, that's just, well, that's nothing. And then this two-fold rotation around the z-axis, reflection around the y-axis, reflection around the x-axis. Those are symmetries. And then you can do 90-degree rotation and time reversal symmetry. This way, reflections, etc. And this basically suffices
Yeah, you're back online. Yeah, you went off for a few minutes.
Was I offline?
Now you're online back again. Okay, great.
Okay. There's some problem. I can go on. So yeah, so we're going to use these phones and oh, now it's stuck. Right. Yeah. Couple them to the electrons in the following way. We'll simply modify the hopping matrix elements nearest neighbors in this way. Here is a fold or lattice displacement. Taylor expanding the hopping matrix element in displacements of the lattice. And then quantizing the store vibrations of these phonons and using some simple model for localized atomic orbitals. Not precise, but you know, enough for our purposes. And was there a question back there? Everything's fine. That gives us a coupling constant between you know, the band electrons. So we go from this basis here down to band electrons, and then introduce this standard formula for the displacement, compact displacements of atoms. Tree for wolf, and you get an effective interaction out of this exchange. This guy has a lot of case-based structure. Firstly, because you know this has some momentum structure, and then the projection from the orbitals, atomic orbitals, down to the bands also yields considerable momentum structure. So this coupling constant is something that depends on both incoming and outgoing momentum. And that's important here. So that fact, coupled with the spin structure of the Fermi surface, which is altermagnetism, is what makes this whole story work. Bottom line is you solve some linearized equation. Here is the density of states. You know, let's say that this is upspin, this is downspin. I've just plotted it now for two different parameters of this next linear coupling. It's a slightly different shape. I'm not saying that it's different from up and downspin. I'm just illustrating it for downspins here and upspins here, two different cases. And so and what you can see here is that if I take this, for instance, now with this next nearest neighbor hopping, the interaction has p-wave symmetry. It's odd parity symmetry. And so that has implications for what sort of momentum structure this gap has. Superconductivity turns out to be, again, if I look at this is upspin, downspin. You can see that it has opposite parity going from k to minus k, but it's higher than p-wave because it has several zeros on the Fermi surface. Several zeros on the Fermi surface. So it is odd momentum pairing. It has to be because it is spin triplet polarized to pair, but it's higher momentum state than p-wave. Tc as a function of chemical potential. Tiny, this is BCS here, and it goes up, and then you sort of lose something at the end. The reason for this peak is that you have these flat bands. And the flatness of these bands, this was this discussion point this morning as well. This is, of course, dependent on details. I can make them less flat by having next nearest neighbor hopping, etc., etc., etc. So there's nothing generic about this flatness, but it's nice to have it to get the large density of states, to get large Tc. Of course, then Eli Ashford comes with its own little thing. Oh, yeah, this is just done. Anyway, here's the reason why this interaction actually might give you higher momentum pairing. If you what I'm going to say now doesn't prove that superconductivity exists, but it rationalizes why it can exist. Suppose I take this AB thing, that's this arc. I now put the K over there in the middle right there. As I said, the interaction depends on both incoming and outgoing momenta, or if you will, incoming momenta and momentum transfer. I start over here and I deviate from this K point and I get the momentum transfer. In this case, it's very, very symmetric. So when I integrate over this whole thing, basically it averages to zero superconductivity. If I move it a little bit of some symmetry direction, it's no longer symmetric, and I can actually get something that integrates to non-zero stuff. In other words, a non-zero gap. So the momentum structure of the coupling constant to the electrons is vital here. So this makes it by the skin of its teeth, superconductivity, with one phonon exchange, spin triplet pairing, spin polarized pairing. Unfortunately, of course, when you have these sort of things, that could be several zeros on the order parameter. It's not a complex gap. It's very susceptible to disorder, but it's getting there. Could we do spin singlet pairing? Right. Yes, I have to do this final momentum pairing. Unlikely, because effectively what you do is to shift the Fermi surface by some amount, and you can see that there's zero phase space for scattering here. So final momentum pairing is very unlikely. So with that, I think I thank you for your attention.
Please, questions?
So one question could be, is there a generic difference between superconductivity and this equal spin pairing between a ferromagnet and altermagnet? Or are they, because I think in the ferromagnet probably also you can get away with just a phonon exchange, right? Yeah. So is the altermagnet conceptually or in practice different from ferromagnet?
Well, I would say yes, because the spin structure of the Fermi surfaces are vastly different. They're not uniformly up and down on the ferromagnet. They're just band split, right? Mm-hmm. So I was simply, you see, in this case, in the ferromagnetic case, you take your degenerate band and you split it by magnetic field effect essentially, so you get a small Fermi surface and a big Fermi surface. Right. Here, so it's hard, I guess, to and then so the difference would be that in this case you will get up polarized group pairs and down polarized group pairs no matter what the chemical potential is. Right. You would not get that in a ferromagnet because you would block up one band. So that's the difference. Yeah.
I have a naive question about who the Ferrel state. Is it because we have spin splitting, so is it a possibility of all the magnets for the Ferrel-like state?
Well, I think it is in principle possible via this mechanism.
Okay.
Because yes, but you see, you have to use a microscope to see the phase space, right? By the way, the cartoons that were shown this morning, you had an ellipse this way with upspin and an ellipse this way, and you can make them more or less circular, right? By a tiny amount of momentum transfer, you can make large patches of those ellipses overlap within a finite bandwidth. That's much more. Okay, I agree with that statement. In that case, for such a model, a fully parallel state would be very viable. For this more microscopic detail model, there's zero patch overlap. Yeah.
There's an online file.
Yeah.
Online.
There was one over here.
Yeah. Oh, you started online?
Okay.
Yes. Okay, start online.
Yeah.
Online question.
Oh yeah. Okay. So Asle, thank you very much for a very nice talk. So in this case, when it comes for the formations and irregularities in the samples and the model system, how stable would the TC be towards that?
Towards what?
The strained or different domains and things like that you have in the system. Because we probably want to have like an altermagnet to begin with that can become a superconductor, but then do you need to have a single domain type of physics to actually be able to contain it, or is the pairing irrespective of the domains?
No, I mean, that's a good question. I think at this point, I'm a theorist, so I always do stuff which is I aim to do intrinsic stuff, meaning that certainly this is single domain, no impurity stuff so far. I have to be honest about that. But I'm interested in sort of predicting things which are intrinsic to these altermagnets.
Yeah,
So
I
definitely,
think it's totally clear, and that's very nice, the result in that sense. Yeah, that they will be there. It's just from the point of view of the robustness. Once you start trying to aim for materials that will show the effect or not, that I think those questions need to be asked as well. Yeah.
Absolutely. I'm totally aware we're trying to sort of do things in steps, but I would totally agree with you, Haro. And this particular superconductivity that we're predicting now will be very susceptible to disorder, simply because the nodes on the firmer surface, there's no Anderson theorem protecting you, right?
Correct.
It would be so much nicer if there had been a complex gap, Px plus IPy. That's never zero on the firmer surface, right? So that would be okay.
Yeah, but I totally agree that first things first. If the answer is no in your first approach, then it's no. But then being yes, then the next ones can be added. Yeah, but very nice, good result.
Thanks for your talk. I have more or less technical questions. So you showed a lot of equations and a lot of graphs. I saw band structure, the phonon coupling, and I have a question: did you plot them by some differential methods or by your calculations, or you do it by some packages like WASP or Quantum Express or some other?
Yeah, so we have our own graphics packages, but these are not our own. I mean, it's basically online stuff that we use. It's Christian or Christopher who made these things, but these are, I would say, commercial.
I mean, you took the equations, then you solved the equation
Yeah,
by
yeah.
yourself, or you just took like some density perturbation theory to.
No, but these are plots of real solutions to these equations.
These are all models, so there's no DFT going on.
Maybe you can do
Yeah, there's no DFT, that's for sure.
Yeah, it's possible to reproduce some results with.
Yeah. So, I mean, if you read our papers and you do, I mean, so I think the information given in the papers allow you to totally. By the way, there are large supplemental materials given. There are zero details in my talk. There are lots of details in our papers.
When you mentioned superconductors, yeah, and for BCO, for example, if we consider copper oxygen chains, will it, or I don't know, whether in chains are antiferromagnetic or not?
I don't know.
Copper oxygen chains, And
Why BCO, yeah.
actually stripes.
Long discussion.
Stripes, it is not discussion.
Like Bermin, Wagner at zero temperature. Yes.
One more last question.
Question more or less out of curiosity. So you mentioned that the gap symmetry, the superconducting gap symmetry, is something of a higher order than P wave.
Yeah.
And you showed the nodes on the order and so on. But I'm just curious, what it is exactly? Is it F wave or like G wave or something?
So you have to count the number of nodes on the firmest surface, right? Where was it? For instance, here. This would be, I would say, what's the next after P? F wave?
F, yeah.
SPTF.
Yeah. So that's the next one. Yeah.
Right.
You just
And
count the nodes.
And this type of lattice coupled with this phonon mechanism uniquely leads to this specific type of symmetry.
Do I need?
Uniquely leads to this specific type of symmetry.
Well, no. You see, the point is that what we need, the only thing we need to, the only thing we can say with this pairing principle, opposite momentum, spin polarized firmer surfaces, is that I have odd momentum pairing. That has to be. Beyond that, it's anybody's guess because it depends on details, in particular what the chemical potential is.
Yeah, so particularly P wave is not forbidden, right?
P wave, with regard to Haro's questions this morning, my question to Haro, which I may have misunderstood what I was talking about, but nothing preventing P wave here. Yeah.
And I fully agree with what you say, by the way. There's nothing preventing the P wave. I agree with that statement of yours. But I didn't talk about P wave superconductivity.
I understand.
Yeah, it seems that we have more questions, but we should move on. Vladimir, you could discuss during the conference.